Let's take a look at our homework from page 186 that we had last night, starting with question number 1. We want to find the coefficient of static friction if there's a toboggan in example 3.18 that's 20 kilograms, forms an angle 30 degrees with the horizontal. So here's our hill, here's our toboggan. I'm just going to draw it as a box because it's easier. The angle from the horizontal is 30 degrees. And the mass of this thing is 20 kilograms. We want to find the coefficient of static friction. So what we're saying here is that this toboggan doesn't move. This toboggan is stationary on this hill. And if it's stationary on this hill, then clearly there's got to be a force of static friction acting up the hill. There has to be, because we know that there's a force parallel that pulls down the hill. And if it doesn't move, then what do we know about those two forces? What's the condition that this thing is in right now if it's not moving? What do we call it? Static equilibrium. And when we're in equilibrium, whether it's static or dynamic equilibrium, we know that the forces must balance. If it's not moving, forces have got to balance. The force down the hill, which is what we call F parallel, has got to be equal to the force of static friction acting up the hill. So I would suggest to you probably the easiest way to deal with this question is to find F parallel. Since we know they're the same, then let's find F parallel. So let's do that now. We've got a force of gravity acting down. I'm going to call that mg, you call it fg, whatever you want to call it here. What else I got acting here? Besides the force of gravity, you got a normal force, and that normal force is acting perpendicular here. Make sure that you draw that normal force the right length. It's got to be shorter than the force of gravity because gravity is the hypotenuse. And it's got to be drawn such that the sum of those two vectors, Nicole, is going to be parallel to the surface there. It's going to be exactly the same as F parallel that I have drawn up here. We also have to make sure that that's a 90-degree angle there. So there we go. We've got Fn right there. We've got Fg. We've got F parallel. And we know that this angle in this triangle conveniently ends up being the same angle as the angle of the hill. All right. So how do we find F parallel? Well, this is just trigonometry now, right? This is, when do you do trigonometry? Is it grade 9 or grade 10? Okay. So grade 10 math, you would just say at this point, oh, look, I got the angle, sine 30 degrees. Looking for the opposite side of the triangle there, F parallel. And I've got the hypotenuse, which is the force of gravity. So I'm going to say F parallel is equal to mg 20 times 9.81 times sine 30 degrees, which ends up giving me 98.1 newtons. Okay. There's my F parallel. What do we know about F parallel? The relationship between F parallel and the force of static friction. It's in static equilibrium, so those have to be, Mallory, the same. So let's say FSF equals 98.1 newtons as well. All right. If FSF is 98.1 newtons, then I can find the coefficient pretty easily here. We got 98.1 newtons divided by the normal force. Oh, wait. Oh, wait. Not quite as easy as I thought, actually. We don't know the normal force, do we? Oh, boy, I missed that one. How do we find the normal force? Sorry? Yeah, we could use cosine. Or somebody mentioned yesterday, I think, that in a problem similar to this, we could use the Pythagorean theorem. That would work as well. Now that we know the opposite side and the hypotenuse, the Pythagorean theorem would work. I would still prefer cosine myself, but it doesn't really matter. Cosine 30 degrees is equal to the adjacent side, which is Fn, over the hypotenuse, which is m times g. So we're going to say Fn is equal to 20 times 9.81 times cosine 30 degrees. What's that one equal? 20 times 9.81, 200 times cosine 30. Is it 173.2? 169.91? All right. We divide those two numbers, and I think when we divide those two numbers, we end up getting 0.58. Is that right? Guys, listen, this is the perfect question to start with this morning. Why? Because I started doing some things. What have I told you guys a million times? You're not sure where to go with something. You're not sure how you're going to solve something. Just try things. Okay. I actually thought I knew what I was doing on this question when I started off, right? I was going in a certain direction, and then I realized, oh, wait, look, I'm missing something. Was it the end of the world that I was missing something? That I didn't have the normal force that I needed to plug into here? Not at all. What did I do? I just said, well, let's find the normal force then. I wasn't thinking ahead of time that I was going to need to find the normal force. Some of you guys may have been thinking that. Sometimes I do this question, maybe I will be thinking that. This time I wasn't. I just ran into a little bit of a roadblock. And what did I do? I solved it. I fixed the roadblock without panicking about it. Just saying, well, okay, if I don't have Fn, then let's find Fn. Let's do it using some trigonometry that we learned back in grade 10. Number 2 says an 80-kilogram skier on a slushy surface starts moving down a hill, forming an angle of at least 25 degrees at the horizontal. What's the coefficient of static friction, and what's the maximum force of static friction on the skier here? Do you know what my gut feeling would be? That I would actually solve for B first here, the maximum force of static friction. That would be my gut feeling. But sometimes my gut feeling isn't right. Sometimes I start solving a question and I realize, oh wait, no, that's not the way it is at all. Whatever. I'm going to start solving this and see what happens. See if I'm right. See if I'm not right. We got an angle of 25 degrees. So we're going to raise the incline here. At 23 degrees, it doesn't start moving. 24 degrees, it doesn't start moving. 25 degrees, all of a sudden the skier starts going down the hill, right? Tomorrow we're going to do an activity that's almost exactly like this, except we're not going to go to a slushy snow hill, ski hill, and stand on skis. We're just going to have a block on an incline, and then we're going to raise the incline until it starts moving. Okay, until it starts moving. And we're going to measure the angle at which it starts moving and basically do what we're doing here, except via a graph. All right, here's my 80-kilogram skier. It starts moving at 25 degrees. So that means that whenever, think about this, whenever the force parallel, whatever the force parallel is at this point, that becomes equal to the max force of static friction. You remember when we did those static friction problems back a week or two ago, a couple weeks ago? The force that we had to apply to just barely get it moving was equal to the max force of static friction. This is the force parallel that's barely required to get it moving. That's going to be equal to the max force of static friction. So I'm going to draw that in, the F parallel. And I'm going to recognize that if this is the point where it just barely starts moving, then that's going to be equal and opposite to the max force of static friction. Right? If F parallel is bigger, F parallel would be like very, very close, but slightly bigger than FSF max, right? Because if we're at the exact value of FSF max, it still wouldn't move, right? So we have to exceed that slightly, but we call it the same number because if FSF max ended up being 20, then F parallel is 20.001 or whatever the case may be. We say it's the exact number. If FSF max is bigger, then it doesn't move at all. If F parallel is bigger, then it's going to not just barely move, it's going to more than barely move. So we know that these two forces have to be essentially equal. Now, of course, we know where F parallel comes from. It comes from the force of gravity, m times g, and it also comes from the normal force right here that is perpendicular there. And we know that F parallel has to be drawn parallel to the surface, and we know that it has to be drawn perpendicular to the normal force. Okay. I hope I've mentioned this enough times now that you guys get it right every time. The normal force must be at 90 degrees to the surface every single time. The normal force must be drawn front to back for the force of gravity in these questions every single time. And then F parallel must be drawn parallel to the surface so that it's at 90 degrees to the normal force. This is the diagram that you want to see every time, not this diagram. Okay, you don't want to see this. What's wrong with this? This is not parallel. This would still be 90 degrees. This is not parallel. And then this is not a 90-degree angle. Okay, we have to have a 90-degree angle, and this has to be parallel to the surface in order to get the vectors working out here. All right. We know that angle is 25 degrees as well, right? Because it's always the same as the angle of the hill. What do we do next? I don't really know what I'm going to do to find the answer here, but do we need to know? Well, what can I do next? Like, tell me something I can do next. Find a parallel. Is that going to help me? My guess is yes. If I had to put money on it, I would say, yeah, it's going to help me. But even if it doesn't help me, like it's no harm done by finding F parallel. So let's do that. Let's say sine 25 degrees is equal to opposite over the hypotenuse. So let's say F parallel ends up being equal to 80 times 9.81 times sine 25. Does anybody have a value for that? We get 331.6708 newtons. Good, thank you. Let's label that up here since we know it now. 331.6708. Oh, look. What did we say before about F parallel and FSF max? They're the same, right? If this is F parallel that just barely gets it moving, then that is the value of FSF max. So we know the answer to B here. FSF max is the two significant digits, 3.3 times 10 to the 2 newtons. I was right. We did solve for B first. Although I wasn't positive that I was right when I started the question. B says, find the coefficient of static friction. Well, the coefficient, FSF max, is equal to the coefficient of static friction times the normal force. If we want to find mu s, what are we going to need to find in addition to what we've already found? The normal force. Well, we can do that. The normal force is, well, the Pythagorean theorem, or as I prefer to do it, cosine function. Say cosine 25 degrees is equal to the adjacent side, that's going to be Fn, over force of gravity. Attack. Let's say Fn is equal to, what do we got here? 80 times 9.81 times cosine 25 degrees. Anybody got a value for that? Mary, got that one? 711.27 newtons. All right, FSF max is 331.67, and Fn is 711.27, and we end up getting, I think, 0.47 for that. You guys just got a copy of a worksheet on inclined planes. I'm going to ask you guys to work on questions 10 to 14 on that worksheet now, please. All right, I've got one more example for you here today, and this we're going to end it today is after this example. This one says a 20-kilogram wagon is being pulled to the right with a force of 100 newtons at an angle of 30 degrees above the horizontal. There's a 50 newton force of friction acting on the wagon. What's the acceleration of the wagon? So let's draw this one out. This one's going to look a little bit different than anything we've seen, although it's kind of a combination of some things. Here's the wagon. You guys know that when you pull a wagon, you don't go down on your hands and knees and pull the wagon with the handle horizontally like this. You know that you're pulling the wagon as you're walking up like this. You're pulling it with a force of 100 newtons. We'll call that FA is 100 newtons. Okay, we also know that there's an angle here of 30 degrees above the horizontal. And we know that there's a 50 Newton force of friction acting back this way, opposing the motion. Now, let's assume that this wagon is not going up into the air. Okay, let's assume that this wagon is moving horizontally, right? When you pull a wagon at an angle like this, you walk with your newspapers in the back or your little brother in the back. You know that it's moving horizontally, right? So what do you think we're going to do here? We've mentioned this enough times, not in the context of this question, right, but in other questions. that when we see something and we're not sure exactly how to solve it, we do something that we know. Okay? Tell me something that you know here. Something that you can do. Even if you may have this great insight right now as to how to solve this problem. And if you do, that's fantastic. If you don't, that's perfectly fine. But everybody in this room can look at this, and if they take a step back from it, can do something. Okay, tell me something, Bruce, that you might want to do here. Find F parallel here. You mean like on our inclined plane thing? Like, okay, we don't have an F parallel here because we're not moving up or down a slope, right? F parallel goes when there's gravity and a normal force combined that are causing it to move parallel to a hill, right? This is moving parallel to the surface, right? So it's moving on a flat horizontal surface, which is good news for us because that actually makes it easier than finding F parallel. Yep, go ahead. Okay, Kelly doesn't like funny angles, so let's get rid of a funny angle. Let's go off to the side over here. Let's go off to the side, draw that 100 newtons at 30 degrees here. Boy, it's been a while since we've had to deal with that, right? Let's call this one, Kelly, Fx, and call this one Fy. Let's make this angle 30 degrees here. Let's say cosine 30 degrees is equal to Fx over 100. So Fx ends up being equal to, what is that, 86.6, I think? And let's say sine 30 degrees is equal to the opposite over 100. So Fy ends up being equal to, what do we got there, 50 newtons, I think? Okay, good. Good. I like that. Is it going to be helpful to me? Don't know for sure, but probably. And even if it's not, he hasn't done anything wrong, right? Take a risk. Take a chance. Calculate something. What now? What do you want to do now? Draw what? Okay, so let's replace this with Fx and Fy. Is that what you're saying? Good. Yeah, I like that too. Going to help me? I don't know, but it's really not going to hurt me. Here's Fx, and its value is 86.6 newtons. And here's Fy, value of that is 50 newtons. So basically, like when I pull it at that angle of 30 degrees, it's like I'm pulling it horizontally at 86, and somebody else is pulling it vertically at 50. Holly, question? Or a contribution? Yeah, it would be sine. It would be sine because sine 30 degrees is equal to opposite over hypotenuse. If you use the tan function, Holly, then you'd have to use opposite over adjacent, right? Which you actually could do since you found the adjacent side, right? But I'd rather avoid that in case I made a mistake with Fx, right? Okay, anybody want to take a stab at what comes next? Okay, what do you think? Okay, F, you're saying F net is equal to FF plus Fx. What about Fy in there? Okay, Kelly said F net is equal to FF plus Fx. That takes care of the horizontal, but what about the Y component there? Yeah. Oh man, you guys are figuring this whole thing out. I don't have to tell you anything with this. Look, we've got gravity acting down, right? I'm going to draw it up here because it's just more space up there. Gravity acts down. And we do have a normal force acting up. Tell me when to stop drawing the normal force, okay? I'm going to start drawing it. You tell me when to stop drawing the normal force. Right there? No. I should have stopped drawing the normal force about right there. How come? How come, Danny? Yeah, not necessarily the same length as Fn. We don't know if they're the same values, but we know that there is a force acting downwards, which is gravity, and we know that it has to balance all the upward forces combined, right? we have a normal force pushing it up, but we don't have to have a normal force as strong as gravity. Why? Because I'm pulling it up as well, right? That makes sense? It's like when you're swimming and you lift up that rock, you don't have to lift as hard because the buoyant force is helping you. Okay, when we're pulling on the wagon at an angle, the normal force has to push up, but it doesn't have to push up as hard because I'm pulling up as well. I'm helping the normal force along. So in the end, this cancels, but not with just the normal force, but rather with the normal force and Fy combined, right? The total upward, normal and Fy, gives me the total downward. Now what do we have left? Ff and Fx. Just the x component. Just real quickly finish this off here, okay? The net force is 20 times A. The force of friction is negative 50. Fx is 86. And we're going to just solve for A here, right? 36 divided by 20 gives me, I believe it's 1.83 meters per second squared. Does that make sense? Okay, we'll do another one of those tomorrow and finish that off. Your homework tonight is the worksheet that we gave you on the inclined planes.